Okay. 5 past. Time to get started, I think. So, new term with for the streaming setup. So, we'll start with an AV check. Um can we see the screen? Can we read like text on the screen? Can we see me over here? And is the microphone working okay? Doing what it needs to do? All good. Hello everyone. Yes, we can see and hear and see. Fantastic. As I mentioned in the announcement, I'm gonna try and preserve my voice as much as I can. I actually I got a message from Andrew, who said that he thinks there might be some throat sicknesses going around at the moment. So if you're feeling unwell, go see a GP, and stay home from uni if at all possible. Hopefully some of us, I'm sure some people had to come into uni regardless, but hopefully some of us managed to stay at home and skip some of the awful weather we've been having today. Is anyone actually at the room, like the room that we usually have the lectures in, out of interest? If you are, and there's other people sitting there confused, like where's the lecturer? It'd be awesome if you could just tell them go check the announcement, that kind of thing. Yeah, and to be clear, I'll say this immediately. We're gonna just do the same thing for tomorrow as well. We have another live stream set up for tomorrow. And so yeah, we'll be a little bit online this week. Luckily, I have most of the setup all still kicking around from 22T3 originally, and it looks like it's mostly working, so thank you everyone for joining. It's a totally different format. Obviously, communication, I think, is not quite as effective online as it is in person generally, but online has all of its own other kinds of benefits as well, in terms of how we can, how I can present and how efficient I am, sitting at a desktop with all these screens and stuff versus a tiny little laptop and everything like that. So, ups and downs, and we'll try and take advantage of what we are able to take advantage of. Now, I'm sure there's going to be plenty of questions around, is this thing not quite work? So we have is the exercise marking system currently down? You submitted them last Wednesday and they haven't been marked yet. In theory, if it was working correctly, they should have been marked already, so almost certainly a bug. We were trying to improve some things with it for this term, so I'll go talk to the admins and we'll have a look at that for sure. It's not going to be your fault, don't worry. Cool. So, as usual, do we have any questions or any interest things that you're interested in, vaguely relevant to what we're talking about today, that you'd like to have presented during this lecture? While you think of if you have any questions or anything like that, I'm going to run us through what we're hoping to get through today, and we don't need to rush to fit things in or drag past 8 p.m. when everyone wants to have some dinner or go to sleep. And so if we don't get through everything, I'm totally okay with that. It just moves into the next lecture. But what we're aiming for, ideally, would be, we just missed this little bit here, wanting to talk about matching, this idea of patterns and how we can match against patterns. It's a really powerful feature. There was this whole thing about optional values, which there looks like there's a lot of slides here, but they're actually relatively quick. And it's just like our first little glimpse into contrasting some different languages and features and all that. And then, once we've gotten through that stuff, we're hoping to just talk about collections. And you'll see that there's really not many slides here. It's very, we're aiming to have it very practical and contrasting some different approaches to working with collections, especially with iterators and imperative styles, functional styles. So just playing around with a lot of code, basically, which is why, again, we don't have many slides. Yeah, and hopefully it's a bunch of fun. Hello. Will there be recordings available on Echo as well? If if that's something that people want, I'll try. At the very least, it will be available on YouTube, like where we have the 22T3 lectures. And if you go to this here, oh right, okay, that's my mistake. There should be, I'll patch the infrastructure after the lecture. There should be an extra column here that says like a link to a YouTube VOD, like a YouTube recording, and you can view it on YouTube if you'd like. But if Echo allows me to upload a manual video, which I think it probably will, but if it allows me to, I can also pull down the YouTube video and upload it there as well, if that helps. And will the deadline for week 1 exercises be extended if the continuous marking system isn't working close to the due date? Mainly asking in case of edge cases. Yeah, sure, no worries. Yeah, that'll be fine. In fact, we usually end up extending it anyway, just in case. Sometimes we have students who join the course a little late, like during week 2, so we'll probably extend it anyway. Let's be real. Cool. Okay, so again, if you have more of these questions, then just keep them coming. I'll keep an eye on the live chat over here. You're welcome to talk to each other in there as well, and I'll try and do my best to filter out, what's meant for me and what's not. But otherwise, I suppose let's get started. So, first of all, we want to talk about match, and I have a few of these dot points to get through. But the most important one here being this idea of pattern matching. So to talk about pattern matching, I think we'll first talk about what a pattern is. So a pattern tries to describe the shape of some data. Right? Tries to describe the shape of some data. So let's maybe, I don't want to do it in here. Let's go, why not use experimentation? So this is what we were using from last lecture. We had a few different, bits of data to play around with over here. And in particular, let's just use something like option as an example to try and start to talk about what pattern matching is, or what even a pattern is. So we know from the previous lecture that there is this thing called an option, right? Option of some type T, and it's either nothing, none, or something, some T. Yeah, over like that. So when we're defining an option, I could either say, let my option, and let's say this is an option, because you need to say what kind of, an option of what. It's a what that may or may not be present. Let's just say an option of an integer, for example, option of I32. I could say this is some value, and I need to provide the value in here, like sum 100, like that. If I forget to provide forget to provide a value like this, I get an error. This will all be an error if I forget. So I need to provide that value. Or I could also say that there is no value, right? Specifically because it's an option. It might be there, it might not be. Now, I can also do a pattern match on an option. So we've seen things like if, we've seen while, we've seen for, we've seen loop, all these control flow operators in Rust. There's another really special, really fancy one called match. Match is great. Probably my favorite operator in Rust. So what it looks like is you say match, and then you say what you want to match on right here. So, usually some variable, but I could say match on like, some function that I call that returns a value, and it'll match on, whatever this function returns. In the same way I could write if, this sum function returns true. But keep it simple, match on my option here, and I'll immediately get an error because I'm missing these match arms. So let me just get it to generate the code for me. If you're in like Vim or Visual Studio Code or whatever, you can usually press some key combination to get it to suggest things to do for you. In my editor, I have Alt-Enter set up. I think in VS Code it's maybe Control Dot or something like that. Play around, you'll find it. Often you can get Rust Analyzer to fill the match arms for you, and it looks like this. So what Rust Analyzer has done for me is it said, my option is going to be in one of two formats. Excuse me. Either it'll be something, and it'll have some value, or it'll be nothing. If you've seen like switch case, like a switch statement with all the different cases, it might look kind of similar to that. But this is kind of like switch case on steroids. Switch case, but like leveled up. Because what can I do here? I can say match on my option. It's either going to be nothing, sure, or it'll be something. And I can put in like, you know, value here, say some value. And let me just change these to-dos here for, let's say, code blocks. Like that. And there's so many warnings going on just because I'm not like, it's saying, hey, this code is unused. You're not doing anything with it. I know, it's on purpose. Okay, there we go. Just like this. So match on my option. If it's something, then it'll have a value inside it, right? And I've just written like lowercase value here. And what Rust says is, let me match, say, this value or this value, depending on, you know, if I commented this line out or not. Oops. Match this or this against these potential branches over here. So if we see how I've got it right here, where it's equal to none, it's not going to match some value because the data doesn't look like that. It's not structured like that. But it does match none. These are clearly the same thing here. So we go into this branch and say println the value was none. Like that, right? Let me do like an if true return over here. Lec materials cargo run, and we see that the value was none, right? Now if I comment this line out and I run it again, you see we didn't end up in that branch this time. There's no output here. In fact, what I can say is println the value exists and it is value, like that. So in this branch, I implicitly have this value variable being declared, which I'm then able to hopefully print out. The value exists and it is 100, right? You can even get fancier with this, right? So these are both examples of patterns. However, another pattern I could have is like sum 42, right? This looks like, you know, a pattern that you could fit this kind of data into. So this branch comes first. So matches are, you know, they're evaluated top to bottom. Checks the first branch, then the next one, then the next one, then the next one, so on, right? Now, if it matches this sum 42 exactly, then it'll enter this branch and it won't enter any others. So I could say something like, haha, 42, like this, right? So a really special case, haha, 42. If I change this now to be 42, you'll see we hit that first branch over here and we don't enter into any of the others. The important thing, what I want to sort of make clear here, is that this, and this all are patterns as far as Rust concerns. And a pattern at the very core of it says, take some data that exists at runtime, right? Some data, we might not know what the exact state of the data is, which we match on, and then check, does it look like could I fit this data into looking like this? Could I fit this data into looking like this? Could I fit this data into looking like this? So on and so forth. And it allows us to do things like leave certain things blank for Rust to fill in with a variable. So if I said, imagine it almost like an equation. I have sum with the value 100, and I try and match that. Imagine match is like a mathematical operator here. Match that against sum value, right? How do I make these two things match? Well, you have to ask, first of all, can they match? And if they can match, how can I make them match? And the answer here is yes, they absolutely can match. And the way that we make them match is we say value must therefore be equal to 100, right? As like almost think of this like an equation, right? Solving for x, solving for value in a certain sense. And so since Rust solved for value here, we'll have value available to us as a variable to use further on. And match really works for basically any data. So it doesn't need to just be like an option that could be one thing or the other. I could match, say, on the number 42, right? Match on 42. And it says, you know, missing match arm, this type here, 42 is of type I32 is really big. I would actually have to cover all these branches. Check if it's 0 and like do something to do. Then check if it's 1. Then check if it's 2. Then check if it's 3, and so on. I'd have to check every branch because in Rust, matches must be exhaustive. So I have this over here, exhaustiveness. Matches must cover all possible cases of whatever input value they're consuming, right? So in the case of an I32, I'd have to cover every number from -2 billion to +2 billion, right? So that way, whenever you match on something, you know you're going to end up in one of these blocks for sure. And Rust checks that that must be the case at compile time. If it thinks that you've, you know, if it thinks that you've broken that promise, it won't let you build your code. Now that seems crazy then, like how am I going to ever match on any kind of integer if I have to cover all the integers, literally all 4 billion of them? And the answer is, well, one answer is that you can also have catch-alls in your matches. A catch-all says, you know, whatever else it might be, I want you to catch this branch. Now, what I therefore need to do, if I wanted to make a catch-all, I would have to create a pattern that can match anything. Right, a pattern that no matter what data I give it, it'll match that data. Now, if I went back to this example over here, you'll actually see there's a trick I can use to make that happen. Imagine what I cared about. Let's say over here, we'll get rid of this 42-bit temporarily. Let's say I didn't really care what the value was. I really just cared whether the value exists or not. Now, in this sense, I've created a variable named value that I'm not even using, right? There's like, your code would be a lot less clear if you just randomly said let x equal 42 around the place, never actually using x. It's not a good idea to create variables for things that you never end up using. But that's exactly what we're doing here. We're saying make a variable value that represents whatever value was inside that option. So if you say, I want to match something that looks like this, but I don't care about what's inside. I know something will be there, but I just don't care about what it is. There's a pattern for that, and that's the underscore. So importantly, I couldn't just say sum because if I go back to this, and I've lost my pen, trying to match sum of 100, you know, match that against sum, these are just not going to match, right? These bits match, but then where does this stuff go over here? Doesn't make sense. Similarly, if I had parentheses like this, you know, these patterns just don't match. Like the parentheses will, but this thing has to go somewhere in here and it just doesn't fit. But if I put this underscore in, underscore is like saying a variable name, but saying I don't care. Like I don't actually want there to be a variable. I just am ignoring this. Then it's great. This all matches over here. You know, this parenthesis you can imagine matching over here. And then the 100 matches into this wildcard pattern. We call this here a wildcard, right? If you've heard of like a wildcard in, you know, Uno, the card game, sure. Like that's, you know, that's what we call this, a wildcard pattern. It matches anything. So this code I could write like this, and this would end up working. Now, if we think about this, this wildcard said match anything. So if I wanted to say match on 42, check if it's the number 0, 1, 2, or 3, and then in any other number's case do something else, I could write something like this. And now Rust is happy. I've covered all the cases for all the numbers. It's either 0, or 1, or 2, or 3, or any other number. So sometimes it makes sense to have this catch-all wildcard case at the bottom, but you want to be a little careful with it, I would say, in general. It's easy, like it's good to take advantage of the fact that Rust makes sure you've dealt with every possible case. And as soon as you put a wildcard pattern in, you lose that guarantee because you'll always match every case by default. It's really quite handy. Imagine if we have this car brand enum and I want to match on it, right? So let me, in fact, do that. Where have I got? I've got one down here. Match on this brand. I can then say fill all my match arms. If it's a Toyota, what do I get again? Toyota gives me a number, Nissan gives me a string. So if I say Toyota with my number, Nissan with my string, then do all these things. If someone came along and said, oh, we have a new client, you know, that we need to aggregate cars for, I got to come up with another car brand. Let's say Mazda, right? They add Mazda in here, and guess what? Any place where we haven't properly dealt with the fact that Mazda might exist, we get a compiler error. And the compiler will go, hey, I'll generate the code for you, you know, and let's make sure we don't end up with a bug because you forgot to deal with this new thing that someone wrote in. So that's actually quite a convenient feature to have available. So be sparing and careful with where you have these wildcard cases. Another cool thing here, notice that when we have a Toyota, it's an option of an I-32, right? Remember we matched on an option and it looked like this. We can do a similar thing over here. So we could say match on a brand where we have a Toyota and it's specifically some number, right? Or, and then in the other case, match on a Toyota where there's no number, like that. This also works. So the pattern system is not just like one-dimensional, where it works in the very first outermost case, but then it just stops like thinking from there onwards. It's really a well-formed total system where we can go and put patterns inside patterns, you know, pull out the variable here. You could have like multiple things in here, like if the Toyota also had, it was like a tuple of an option and a string, something like that, then I could have two variables in here. Toyota is a tuple of an option and, you know, another string over here. This would also work. So it's a really powerful concept. It might be uncomfortable at first and it might be a lot to learn, but it's, you know, it's a really powerful tool to make use of. It's also how things like, if I have let x is 42, let y is 1, 2, 3, and I want to swap those variables around, right? I want to say let x be y and y be x. That's also how we can do things like let xy equal yx. You might remember in the first lecture, or maybe the second lecture, I told you that let statements actually don't take a variable name here, they take a pattern. It just so turns out that a variable name also is a pattern. Patterns are more general than variable names. And this is how we're able to use tricks like this to say, create a tuple of the values y and x, and then pattern match that tuple against this pattern, right? So x has 42, y has 123. Remember that for a second. Let's go into the whiteboard over here, or the blackboard. So x has 42 and y has 1, 2, 3. I say let x y be equal to, you know, yx. Then what that ends up equaling is 1, 2, 3. Oops, 1, 2, 3, 42, like that. And then we pattern match this data against this pattern. And what we find is, yeah, we can solve this. X matches with this 123, y here matches with this 42 over here. And so they end up getting swapped values. And you can continue to like iterate on this. Patterns can be really powerful. Okay, a lot of talking. Let me catch up with the chat here. How would you decide whether to use this over an if-let? They seem to almost do the exact same thing from what I can see. Yeah, that's absolutely true. There is another thing I haven't talked about yet called if-let, where we could say, with this option, let's say we only cared about the sum case. We knew that that we're not going to do anything in the none case. It's going to look just like this. There is a slightly more concise way of saying this, where we can say, if let sum something be equal to my option, like that, then print out the value exists, like this. So this and this are equivalent. It's just saying we only care about this specific pattern matching. And if this pattern happens to match, then go into here. And of course, I can use things like variable names in here. The value is this, and the value, and it is value, like that. And this, yeah, this will also totally work. And how do you decide between the two? Really, it's actually just a style thing because they both are functionally the same. If you're going to write a match where you only specifically care about one pattern, probably if-let might be more convenient for you. Does match only compare the type of the variable? So yeah, this might have come a little earlier on, but just briefly, it doesn't compare the type. It really compares the structure of the data. So this is really mostly in the case of like an enum, either like this car brand or an option, where we're comparing the structure of the data. And the structure of the data at runtime, you know, is kind of defined by the type, but is not the type itself, if that kind of makes sense. So it's worth noting that these patterns all need to sort of describe a value of the same type. You know, we only can put in one value, and that value needs to have a known type as far as Rust is always concerned. And then we get to inspect on what exactly is the structure of this specific value. Okay, yep, cool, answered there. If some value is on top of the sum 42, will it still print half 42? Yeah, great question. And I can, why not just show you? So let's do, what am I doing? Where'd my match go? Oh, I was using this one. So I have, let's say, some value and then some 42 specifically. And let's say the value is value, and then this one just prints 42. What we should find is we get the value as 42, not 42 itself, because it only finds the very first branch that matches and then ignores the rest. I bet if we turned, if we used like a linter or something, probably if we ran something like cargo clippy, I would be surprised if it didn't notice, if it didn't, it's got a lot of other stuff going on. It may or may not notice. There's other like, yeah, there's like clippy pedantic and stuff like that. There's probably a lint that would spot a scenario like this where this match case is never going to get hit. Actually, it might even fall under unused, which might be why we're not seeing it. But in any case, does the order of the match case matter? Yep, because it goes top to bottom. Can we match on expressions? E.g., the value is less than 42 and greater than 5. So yeah, there is a extra sort of functionality in patterns that you can also use, but is sometimes a little confusing. You could say match on some value and then add in what's called a match guard, where I can say some value if value is greater than 100, like that. Now it's saying I'm not covering all these, you know, I haven't covered from any number less than 42 in like a sum. So it's noticed, you know, you have more work to do. But you can, yeah, you can add on these match guards, as they're called. And they can be helpful. Or we could also change the pattern itself. We could change the pattern itself to be some value, like where it's 42 onwards. So this here would be a pattern saying some number from 42 up till, you know, infinity is not really the right word for it, but up to the maximum number, effectively. Or I could say like 42 up to 100, for example. That's a pattern I could use. Then you might go, well, what if I actually want to know which exact number it is? And there's more stuff you can do for that. You can write value at 42 up to 100. It gets, you know, they're quite complicated. There's a lot of stuff you can stack on and stuff. Yeah, you'll just, I think it's easiest to just play around with it yourself and, you know, do the Googling when you think of something that you'd quite like to use. So match is basically used as a comparison. Yeah, you're basically comparing data to, you know, what kind of structure, what kind of state you think the data might be in. Instead of a wildcard, I used an X and it still worked. Why is that? Yeah, great question. So if I have, let me undo a little bit back to, let's say here. Let's say my wildcard case is down here. I can absolutely change this underscore to hello, and this will still work. Because what's going to end up happening is it's going to match, let's say, none being the data against a pattern of, let's start with the underscore. Underscore and none, do they match? Well, of course. The underscore will fill in this none value, and you just won't have a reference to be able to use it. But if I wrote, well, not value, let's say I wrote hello instead, these also match. Because this here is just a variable name. If it was something that wasn't a variable name, like it was like student, or let's say foo down here, Rust wouldn't be so happy. Like if I said it was foo with an X and a Y inside it, like it saw that this is not a variable name, Rust would not really be very happy. You can see it's getting an error here. But if this is just a variable name, hello, it's working like an underscore would. Right, it's working like an underscore would, and I would just have this hello available to use. So I could say print line value equals hello, like this. and then cargo run. Oops. The value wasn't none, so I'll actually make it be none. Right, and we see value equals none. So this is working just like the underscore case in the same sense that this and this, you know, are kind of doing the same thing, just binding a variable or not. Onto the order question, does the order of match cases impact performance? E.g., if I put the case that gets called the most often at runtime all the way at the bottom, is that less efficient? Yeah, in theory. It'll have to check the cases before it. That's correct, yeah. So it's more like case conditions in Python. Yeah, that's a reasonable comparison. But again, very like the power of these extends quite greatly. Will these variables and patterns where matching be accessible outside of the match statement? Yeah, no, they won't be. Because let's say I have value in here and hello over here. Am I going to be able to use value and hello out here? The answer is we don't really know. Right? If I try and like print out value like this, we don't know whether when we went into this match it happened to go into here and get this variable value. So this thing, like, first of all, Rust has like scoping rules, so that variable is really only going to exist for this scope here. But even if it didn't have this scoping rule, even if it had global scope where variables were, you know, were allowed to exist forever, we wouldn't know whether this variable is actually present or not. And because Rust doesn't have like null or undefined or anything like that, anytime we have some sort of value, it must always be present. In this case, value and hello may or may not be present, so Rust couldn't reasonably say that you're allowed to use those variables outside of it. Yeah, but great question. Cool. I think I've more or less caught up on the chat there. Sweet. What else did I have over here? Matching on an option and matching on a result as well. So I've matched on an option a fair bit. I'll just briefly show you what matching on a result might look like. So results are actually very similar to option. Over here. This one is either nothing or some value t. A result is either some OK, like some value t, or error with some, you know, value of type e. So the difference here is that an option, it's either giving you the t, like here is the value, or there's no value at all and no data. A result is much like an option where it might have an OK value, it might exist and have a t for you, but if it doesn't, right, in the none case, you can also attach some data, right? You can say error and here's some sort of error value, say like an error message or an error enum or something like that. So if I have something like, let's go here, let my result be equal to OK with the value 42, I could say match on my result. And let's say this was a result that either has a number or like a error message, which is a string. Fill the match arms. And this here I say OK number or error message like this. Oops. Right, and I could write something like print out, okay, the number is number. Or I could write error, the message is message, like that. Right, if I run this, okay, the number's 42. But if there was some kind of error and I need to provide an error message like, oh no, a really descriptive and useful error message, you'll see error, the message is oh no, right? So matching, you know, looks similar to this kind of thing. If you don't care what kind of error went wrong, you might just wildcard it like this. You just want to see if it went well. But yeah, match allows us to do this kind of thing. You can return values from match statements. Yes. So this is the last important thing I really wanted to touch on, which is that like, you know, ifs and loops and every one of these operators in Rust, match is also an expression. So if I want to say let expression value be equal to this, I totally can. I need to put a semicolon down the bottom, and then each of the branches has to make sure that it's producing a value. So let's say this gives back the value, right? Then in this branch, I say maybe I give back 42, and maybe I want a default value if the option is not present. So the default value might be like 999, which is a terrible default value, but it'll serve my example. Then after this branch, I could certainly print out my expression value that I just created. And you'll see because the value was none, I got back 999 out of that. So yeah, matches are also expressions, just like all those other operators. And this can be a really powerful tool to use. Matches as expressions, that is. And the highest priority pattern is just the very first one. So it'll literally just goes top to bottom through all the match branches. Now, what's the difference between if sum and if let sum? If sum won't compile. So if I say if sum, like, 42 equals my option or whatever like that, this, as far as Rust is concerned, won't be like syntactically valid. You'll have to say specifically if let. You could do if my option is equal to sum 42, like this, with the double equal sign, like that. And those will effectively be doing the same things, but you wouldn't be able to say, for example, if my option is equal to some value, because it won't know what value is. So that's where the power of pattern matching might come in. If you want to say if the option is something, and knowing what the value is out of that. Otherwise, if you weren't doing it that way, you'd have to write something like this. If my option is sum, then let the value be equal to my option dot unwrap. And unwrap is a function that might crash your program. If the option is there, it won't crash your program. It'll just give you the value inside it. But if the option isn't there, then it'll crash your program. Now, in this case, we know it's fine because we just checked if it's sum, and we're working on the same option in both of these. But as things get more complicated, it's very easy to make that mistake, and that's what happens all the time. So using match to avoid the possibility of making this kind of mistake, again, yeah, very powerful. Okay. Lots of match. Match is really cool. It's really awesome. Okay. So, where are we at? I'll give like a chance for any last questions to filter through, but we'll do this like option example, the optional values example, up till the break, take a 5-minute break, and then we'll do the like collections content in the latter hour. Cool. So any last questions about this? I think the chat's relatively quick because I've got it on ultra low latency, stream latency. Are there any advanced match operators or patterns similar to the @ sign that you haven't shown us yet? I mean, we can just go like Rust patterns. Patterns and this is no. I want Rust. Oh, not design patterns. Rust reference patterns. Here we go. And like the answer is tuple matching we've sort of seen, identify patterns we've seen. Yeah, there is some. One that just came to mind. Yeah, like the rest pattern. If you have like a list that you're matching on, you could say any amount of elements and then this one being the last one. Or like this element and I don't care about the rest. Well, I'll call the rest end, for example. There's all kinds of like special things you can do in here. You could do like the penultimate one, so the one before the last one, by saying don't care about all the ones at the start, variable this, and then wildcard out the very last element, for example. But something that came to mind is also ref. Not this one, but ref. Which we'll get, this one, ref over here, which we'll see more of. Maybe we'll touch on this when we talk about ownership and borrowing. But this one is also a little bit special as well. But yeah, so if you're interested in all the crazy ones, the reference would be the place to look. There's tons of like crazy stuff here for sure. Or patterns as well. You can do a pattern P or Q with just a single bar in the middle. Yeah, plenty of interesting stuff to look at here. Cool. So, Optional values. Okay, let's look at optional values now then. So basically what I want to get at here in this segment is talking about the idea of something maybe being present. You know, it may or may not be present. And I previously compiled a few examples. I think I actually had this in Leco 3 as well. Yeah. So I put together some examples a while ago of a few different programming languages that I think are relatively popular. So we have Java, C, C++, Go, Python, and Rust. So in theory, we've all seen C, hopefully. So I'll start with C, and you're going to see that all the programs end up looking approximately the same as this. We have some main function that calls another function which may or may not return a value, depending on a Boolean. So if you call this function with true, it should return a value that is present. And if you call the function with false, it should return like an empty value, a none value, a null value, whatever you want to call it, depending on your language. And I've tried to do this in relatively the most idiomatic way for each programming language. A lot of programming languages allow both like an imperative style and a more functional style. So I've also generally included two methods of destructuring that value once you receive it. So you can see here in C, the most canonical way, you know, the most idiomatic way of representing a value, maybe being present, maybe not being, is by using a pointer. And you have an implicit nullability of all pointers. Whenever you have a pointer in C, you can almost imagine it to be in two possible states, where either the state is it's a pointer to some data, or the state is it's a null pointer with no valid value, you know, like the 0 pointer. Now in practice, that's not quite the case. You can also have, you know, a pointer to some random position in memory that's totally invalid, but generally that means your program has like undefined behavior going on, you know, is a dangerous program already. So we're going to rule in a few of these languages' favor and assume that's not the case. Because it's a little sideways to the point of talking about a value being present or not. So over here it says, if it's true, then return, you know, this hello there string. Otherwise return null, null being the empty value. And so we can say create with true. And one approach we might take to determine whether this value is present or not and then make use of it is in C, we could certainly use if. So we could say if this pointer, right? And when we write if some pointer value in C, that implicitly is the same as saying if create true is not equal to null, then we know create true must be valid to use. And so we can end up using it over here. Otherwise, we'll print out, you know, return some empty value. It'd be a little dangerous to actually just unconditionally write, you know, create true returned whatever the value was. Because if I do, you know, %s with null here, or some other function that's, you know, taking in this kind of value, it might not be happy to receive a null pointer. And you might end up with, you know, in C, a segmentation fault. In some other languages, some kind of exception raised, like a null pointer exception in Java or something like that. So we certainly want to make sure that our value is valid to use first. But there is a connection going on with the human here, with the programmer, in that this line is only valid in the case where create true is not null. I checked that myself as a human, but it's not like the compiler has my back. If I forgot this statement, right, if I forgot the whole if statement entirely, you know, is the compiler going to tell me, hey, this line is dangerous to run? It'll probably just go, sure, I'll run it. And then things will go wrong at runtime, right? Runtime, when your code's been deployed, and you know, you might have users using it, it might really need to stay online. So having the compiler be able to tell you, hey, this might be dangerous, might be powerful in some cases. So for method 2, this is another pretty idiomatic way of dealing with this kind of thing. I've used a ternary statement. Talked about this briefly with regards to Rust not having a ternary statement, but ternary expression really. But you know, under the belief that it doesn't really necessarily need it like other languages might. Here we unconditionally print, but we just substitute a value in, you know, based on this variable. So we say, check whether this is okay or not. If it is, then use it. Otherwise, use this thing. Now, this is potentially a little, it's just really a different way of doing things. If I forgot the empty case, but I remembered that it may not be valid, then it'll help me remember that I need that. This is basically the equivalent of if I forgot the else block over here. If I recognize, hey, the value might not be there. If I forget the else block, compiler is not going to say anything. If I forget the else block over here, at least I'll get a syntax error, and the compiler will go, hey, you forgot to deal with the case where it's not there. So it might be a little more useful in that particular circumstance. But, if you forget to check it entirely, it's not exactly going to save you, right? It'll still just let you write through. Okay. I'm guessing talking about the compiler not being able to tell you things that are dangerous is leading into the Rust compiler warning you about it. Is it actually the compiler for Rust, or is it a static analysis tool that's being run before compilation? So yeah, we will get to Rust in the end and how Rust approaches this kind of thing. In particular, in some cases it will tell you, in other cases it might not. And in all cases, it is the compiler warning you about it. I mean, the compiler really is a static analysis tool at the end of the day, but it is, built into the compiler. It is the compiler itself, and you can't just sort of skip the checks in a way that's like unexpected, I would say. I'll show you, when we get there for sure. Let's have a look at, say, Java, and we'll see a pretty similar, like a similar kind of approach, but with this optional type here. So see, Java does have an optional type, kind of like Rust, where we can say we have an optional string that this function returns. So create taken a boolean. If it's true, return a present optional with the value. Otherwise, return an empty optional. Right, and so we can say create a present optional and do the whole if it is present, then create true.get. So Java, they're working to include some pattern matching things into the language, but it doesn't quite have Rust's level of pattern matching, pulling the value out while checking if it's present like we get with match. So there is, again, that contract between the programmer and what they've written here that the compiler is not exactly checking for. And it does have a more functional approach similar to C as well. Get me like create false or else empty. This is going to say unwrap the optional if it's present, otherwise give me this empty thing. And this is quite convenient as well, because if I forget the or else case, the Java won't compile. If I say Java C option, oh, my mistake, of course, because in the case of printing, it will, because Java's happy to print it optional. But if I accidentally wrote, say, string foo equals, not that one, string foo equals, oh, I've lost it. Okay, create false, like that. It won't be so happy. If I get rid of this plus, try and compile it now, you'll see, hey, you forgot to deal with the fact that it may or may not be here. So it does kind of catch you in that way, if that makes sense. But there is a nasty little corner going on with Java, which is, if we have this optional type, it may be present or it may not be present, right? And a optional with the string or an empty optional, but there is actually a third state as well, which is that the optional itself could be null, right? So when I say option create true equals true, in theory, and this is, it would be generally considered bad if this were the case, you could return null in the empty case. And what you're going to find is, as soon as we call create false and get this null value, whatever you try and do on that option is going to cause some kind of error, right? I say create false and then say dot or else. I'm calling or else on a null value. Java's not going to be happy. It's going to say you're trying to call some function. It doesn't care what the function is. It doesn't care. It's about, checking if a value is not there or not. Sorry, a value is there or not. It's going to say you're calling this on null. I don't know what to do with this. So if I try and run this instead, like that, it's been compiled by Java. What did I have? Java 11. It was compiled on a more recent version. Oh my gosh. All right. See, something's Java 19. There we go. Null pointer exception. Right? Cannot invoke or else because the return value is null. So it can get like, you know, things will certainly break if you ever accidentally end up with a null in place of an optional where you're expecting it to be empty or present. So this really plays into this idea that a lot of languages have this, you know, this implicit nullability, where whenever you have some kind of value in the language, sure, it might be there, but you'll always have to account for the case where it maybe is null. And so when you try and bake in some kind of optional scheme into your language, like Java did, they wrote some code to try and, you know, we've seen other languages with this optional thing, let's bring it into our language. Now, the optional itself could actually be null. Instead of the optional being, you know, an optional that is present or an optional that is not present, it could also be null itself. And so you end up with two potentially bad empty cases, and then you're still stuck doing if create true is not equal to null and create true is present, and stuff like this. So a lot of you know, modern code bases have been trying to avoid null, and specifically annotate, you know, statically in their code any value that may potentially be null and force themselves to deal with it, because it's starting to be recognized in the industry that maybe having a pervasive null potentially anywhere might lead to more likely code failures over time. So that's something that's kind of going on with Java. I'm gonna, like, there's, you know, we have C++, Go, and Python. I'm gonna just quickly run through them and just give you the cliff notes. It's really upset with my C++, because I think it might think that it's C. In any case, try and ignore these errors popping up all over the place. But C++ also has this std optional type over here. C++, like C, does have these this idea of nullability about its pointer types, but not everything really is a pointer type. And in our case, with the optional, it actually kind of works a little better. And so, yeah, we can have an optional of a string and say, create a string hello there, or return a null option. And we have the similar kind of approaches. Check if the option is valid for some definition of valid, as C++ puts it. And then they use something like the dereference operator to get me the value inside of it. Again, same contract where it's not enforced that you need to check this before dereferencing, and you might run into issues if you dereference a null option for sure. Similarly, functional kind of approaches might help out sometimes. In Golang, we have the same kind of thing. Any pointer in Go can potentially be, they don't call it null, they call it nil. Everyone has to have their own little isms. You know, Go calls it func, Rust has to call it fn. Everyone has to make it slightly different, of course, just so it's harder to remember. But so we have check if it's not equal to nil, dereference, this kind of thing. It doesn't really have, Go doesn't have great functional capabilities generally. It's more of like a actual philosophy of the design of the language, is that they just find the imperative approach to be just to be clearer. And so instead of offering multiple approaches, they sort of mandate you have to work imperatively. So we can't really do this whole ternary thing like we did in other languages. We have to sort of mimic it by saying, create a variable, you know, set the variable to this in this case, this in the other case, and then print it out down here. So, you know, something to be aware of for sure. Again, I'm not going to go too deep into all these languages here, but you can play around with this code yourself. Python has implicit none ability. Again, null, nil, undefined in JavaScript. None we have here in Python, where basically any object in Python might be none. And so same thing, check it's not none, use the value. And ternary kind of thing. If this is not none, then give this value back, otherwise give that one. You know, the Python sort of wrapping from the middle back to here, over to here. You either love it or you hate it. It is what it is. But every value might be none. And so you see, like, it's this same pattern across a lot of different programming languages. You know, the idiomatic way to deal with these kinds of things. And now we'll pull up the Rust code over here, and we'll see that we can mimic that same thing in Rust. So we have create returns an option of a string. Ignore this, like, you know, extra stuff going on for the moment. We'll learn about that later. But if it's true, give back some value, otherwise don't. And we have the same thing going on. We can do is some, like check if it exists and then unwrap it, and this might potentially crash. We also have a functional approach over here. Create with, get an empty value, unwrap or provide me this value. But say I like forgot to do this over here. It's not gonna show me here, but you'll see, you can't print this thing out. You forgot to deal with the fact that it might not be there. That is, of course, unless I, formatted it differently, then it would have been fine. It's similar to other languages. And this is where I've got some dots all the way down here that I'll now get rid of. We have this third method of potentially dealing with things where we say match, right? And match sort of all these different edge cases of what we might have screwed up along the way kind of tends to deal with all of them. If we forget to deal with the fact that it might not be there, and I know again it's because it's not in a cargo project, it's not showing me errors in the editor, but you'll see, hey, you forgot to cover the none case over here. Or if I forget the sum case like this, you forgot to deal with that. Or if I just tried to print it out directly without checking what it is, print out create true unconditionally like this, we get a different error like this. Only when you've actually dealt with things correctly, it'll allow us to compile. And now there are ways to get around it in potentially dangerous ways, like this unwrap. But what you'll come to learn is that Rust has a few sort of key words for specifically dangerous operations. So things like unwrap, another really common one is expect. And it's a relatively small set of these, naming conventions, these keywords that you can sort of keep in your head, such that when you see an unwrap, you go, that might be dangerous. Now, if Rust is so concerned about safety, correctness, that kind of thing, why would it allow us to have something like this? And this is actually something that I think is quite a powerful thing about Rust, is that I find it to be a really nice language for, I have an idea of something I want to make. I make a prototype, right? It crashes a lot. It doesn't work for things, but I get the proof of concept out there and I get the working prototype. That thing has unwrap everywhere. Everywhere where I have, some data that may or may not arrive, forget it. I'm dealing with the proof of concept. I want to see if this is going to work. I'm trying to move quickly. Unwrap, 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 right? Or it's very close cousin expect, where I'm saying expect it to be there. If it's not, then some error message like this. Great. So that gets me to a solution quickly because I don't have to think about all the failure cases. But then I have my working prototype. I get the thumbs up. Or maybe it's my own personal project. I'm like, yes, this works. It's going to do what I want. I want it now to not fail. Right? Now I know what to look for. Right? I know I need to look for unwraps, expects, a couple other keywords that you might end up searching for. I could literally do a find. Right? Or I could just scan through my code and have a very clear indicator of this is an operation I need to fix up. The same cannot really be said for, let's say, C. Because over here, okay, this was a string pointer. Maybe an easier one to look at would be C++ here. Dereference, right? Dereferencing was the unwrap in C++. Right? That's not so easy to check every single dereference I've ever done of any pointer and be like, those are what I need to clean up. That's half the application, right? Or in C, there was really no operation in this case. It's often a dereference. But we might just be passing a pointer to something that doesn't really want a null pointer and might cause an error elsewhere. Or, same deal goes with Go, a dereference. In Python, Python's really dangerous because anywhere you use any value, that value might be none and it might be a dangerous operation to do. Right? So now you really have to check over all the code if you want to go from prototype to really robust application that deals with all the failure cases. Or at least when you're prototyping, you need to take really careful note to do zcall of this is dangerous. Maybe this line in particular isn't, but you'd have to really meticulously keep note of where you need to come back to, or at least it's going to be a lot more effort to go from that prototype to the, robust real world application. So again, I have my own opinions about, how these things sort of interact in different circumstances. And I'm not asking you to share my exact opinions. I'm asking you to, listen to the ideas and then experiment with them on your own and then come to your own conclusions. I've tried to put together the sort of rough structure of each of these languages we talked about. So things like so basically what each of these columns, these rows here are saying is talking about how you represent an optional value in each of these languages. So in C, you would use a pointer of whatever type you're interested in, maybe being null, maybe being not present. Implicit pointer nullability is saying that all pointers might implicitly be null. Unwrapping on star and arrow is saying these are potentially dangerous operations if it's not present. What happens when you dereference it? You get undefined behavior. We're going to find some time in some lecture to talk about undefined behavior. It's a whole thing. Robust programs must be defensive. This is a important thing to mention, this idea of defensive programming. If you're not sure where things may or may not go wrong, or let's say in the very simplest of examples, I have a function, that takes in, let's say, some inputs and then returns like some type pointer. My question is, you call this function, let's call it f. You're in your function, you call f with those arguments, and it gives you back that value. Let's say you call it val. Is val valid? Right? Does it point to a valid actual type? And the answer is maybe. I don't know. Right? Like, if the function has a comment that says, blah, 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 like, type, or not type style, like the return value is always valid, right? It's always a valid pointer. It's never null. Okay, you read that as a human and you assume that's the case, and then you don't need to do a null pointer check. But what's to stop them from changing the definition of the function? And now this function maybe sometimes returns null in some case that they didn't consider when they originally wrote it. Right? They go and update the documentation. Sure, okay. They remove that part that says that it's always valid. Your code still compiles, doesn't it? Right? Like, your code is still going to keep on trucking. But the fact of the matter is now your function is potentially dangerous because you're relying on what a human said. Or if you're reading the implementation of the function, the actual implementation details, that's you as a human reading that might change in future. The power of only allowing this nullability through a specific type, right? So having a function that returns type or a function that returns an option of some type, like this, is that now it's represented statically in a way that the compiler verifies. If they go, oh, wait, we've realized that sometimes this type isn't always going to be valid, they need to change the types. Then when you go to compile your application with this new version of the function, it's going to give you an error exactly where, where it wasn't going to work, where you made the assumption that it was actually there. Right? That's something to think about. We're going to talk about this again when it comes to Tony Hoare's $1 million mistake as well. For C++, can't we just have a deref method within the class that returns a deref object, which would be a pretty simple getter? So couldn't we have a deref method within the class that returns a deref object, which would be a pretty simple getter? In theory, you could do that. And I think that would have been better if C++ chose to do that, just personally. The fact of the matter is that the standard library's optional type chose to use the dereference operator to unwrap an option. I think it would have probably been better if it was something like .unwrap in the same way Rust has it, because it would be something to look for when you're going to look for dangerous things. But because C++ doesn't have pattern matching in the way that Rust does to help you extract the value out, you're going to find unwrap all over the place where it is realistically totally valid. There's not like an error case to check for. You've already checked for it over here. So it's Rust it's like twofold, where Rust is able to reserve unwrap really just for those situations where you're not dealing with things properly, because it has tools to deal with this case where it's very clearly been checked for in the way that the compiler, the machine, understands. So yeah, again, just things to think about there. And yes, it does have .value, but there's two ways to do it, so you're going to find it happening both ways. Yeah. So if we use if-let intentionally and not a quick and easy way, don't handle now, would you use unwrap for that? So it depends on what you're trying to do. If you are saying like, I don't care whether there's an error in the sense that like robustly this application, it doesn't matter to this application whether the value's there, whether it's not there. Like I'm perfectly happy for the thing not to be there if that would be good. But when you're writing your code and you go, this actually in theory could go wrong and I'd like to deal with it someday, dot unwrap is useful because it gives you that thing again to look for. The same thing in theory could be said for like dot value and dereference and that kind of thing. And that might be a kind of stylistic approach that you take on within your own like code base. But the good news in Rust is that this is the culture of Rust programming. This is something we'll talk about in the course as well, in that each programming language tends to have a certain culture that forms around it, within which like how programmers idiomatically think about and execute on certain ideas. And that's generally important in terms of the approximate standards of the language, let's say. But again, we won't get too sidetracked with that today. So what I was saying is when I was saying robust programs must be defensive, if you're not sure whether this value that you get back is actually going to be present or not, you end up having to be so defensive in saying, whenever I call a function, check it's not null. Call this, check it's not null. Then do something with that value, check that's not null. And then like I get a list back, check it's not null, check it's not empty, then proceed forward. You end up writing so much code just like check things are all right, check things are all right, check things are all right, all the time. It helps make your code a lot more robust, less likely to crash, more likely to do the right thing, and so on. But it ends up being very arduous and ends up taking over the code base. If you've written, a lot of, languages that suffer from this a lot might be things like C and Java, probably C++ as well. Again, if you're trying to write robust code, you've probably felt this kind of pain before. So when you know that your type will, if you have a T, it's never null. It's always there. It always actually has the value that we're interested in. That can be quite powerful for your own assumptions, and not needing to constantly be so defensive and check like, is that T actually there? I have a T, I know it's there. I have an option of T, I know the option is there, and the option will be something or nothing. I don't have to consider something, nothing, and null, right? As three different possibilities like in some other places. Anyways, I'll let you go through these slides if you're particularly interested yourself. General question, what does an optional value even represent? Some quick answers. You might have a function that maybe just doesn't produce, it might not produce an output. String to int, not all valid strings are going to be valid integers. That integer may or may not, be outputted. A function might not require an input. It might say, hey, this thing is required, but this thing isn't, right? Or some type might not hold some data. A student might be composed of a ZID, a name, but that WAM may or may not exist yet, let's say, right? Notice that these are being encoded in types. If I have a C function, like if I go into this one and I want to use the function stir to L over here, convert a string to an integer, basically, stir to L. It takes in 3 arguments. How do I know which arguments are required or not? Right? How do I know, like, can this be null? Can this be null? Can this, like, what values can this thing take on? You generally need to end up checking the man pages, right? Like, you need to go consult documentation. And what you'll find is that it says converts the initial part of the string in endpointer, that's this one here, to a long integer according to the given base, which must be between 2 and 36 inclusive, or be the special value 0. So it's saying the base is actually optional in a sense. If it's 0, then it's, we'll just default to something else. Endpointer, if endpointer is not null, so endpointer is nullable, so on, and it sort of continues on. And then you look at the return value, and that either returns the result of the conversion, or it might return long min, or if something else goes wrong, it might return long max. It sets something called error number to tell you which error it is, right? So like, there's a lot of human going on here, and humans make mistakes very often. If we can get the computer to do the same thing, there might be a benefit to be had there. Cool. Now, the big question here is, how does language design make writing robust programs easier? And I think the general idea I'd like to suggest is that if we don't need to if we don't need to be so defensive in our programming due to the language design of having implicit nullability whenever we have something like a pointer, or in Python, like implicit nullability over any value, right? If the language doesn't allow for that kind of case, then we don't need to assume that might be the case ever, right? And that, in theory, can make writing robust programs potentially easier. It's up to you. A really useful and important reading here is Tony Hoare's $1 billion mistake. This InfoQ link is probably the best one to look at, where it's really not that long, if I recall. Okay, it's like an hour, but there's like key takeaways here. If you have an hour to spend watching this like legend of the industry talk about his work, it's really worth watching. But he basically invented the null reference, the null pointer, in AlGol W in 1965 simply because it was so easy to implement. And he basically considers it to be his worst mistake in his like programming industry career. And so yeah, see what he has to say about it. He literally came up with it, and I want you to look at that really just to suggest that maybe null pointers aren't a good idea. I'm not saying null pointers are a bad idea. You must hate null pointers. You must use languages without null pointers. I want you to look at that and say, maybe there might be something to be had trying out a language that doesn't include a null pointer. Something to think about. Okay, cool. 16 past. We'll take a break till like 20 past. If you have any questions, type them in the chat. And yeah, let's just take a quick break. We'll come back 20 past, answer some questions, and then look at the collection stuff. Cool. All right, quick break. All right, let's get stuck back into it. And I think in C we can use default, like a default value. And the answer is yeah. And like in some cases we certainly can use a default value, but there's not always like a reasonable default value for things. And sometimes the default value might end up just masking issues that are actually happening. Right? If we say do this thing or provide a default value, maybe that's really what we want to do, but if C, used default values by default in a lot of these cases, where, something going wrong, we really want to deal with that in some meaningful way, have some extra logic that maybe goes on if there's some kind of error, then it would probably get in the way more than it helps us. You might end up having checks to see if something gave a default value so you can deal with that error gracefully. And then you end up with problems where it can be hard to tell between something going successfully and giving this value, which also happens to be the same as the default value, versus it going wrong and giving the default value, which is the same as this other value. There's all kinds of extra issues that potentially crop up that, again, are worth thinking about. Okay, so the good news for the rest of the content that we have here is that we actually got a head start on this when we covered we weren't meant to cover like some of the Vec stuff in week 1, but we did. And so we get a head start on all of this. I got a list of common collections for you to have a look through. You can just go to the standard library docs and search for any of these. Like say, if you're interested in a Vec deck, just search for it. You'll find it here. And there'll be, documentation explaining what this thing is. But the real bread and butter ones that you'll use all the time, arrays, kind of on the half bread and butter. You might sometimes use them, but they're not as common. The really bread and butter ones, Vec, string, hashmap. Those you'll just see all the time. Vec, string, hashmap. If you're good with these ones, you'll generally be you'll be pretty fine. So we just have some exercises to do with Vecs to get the hang of them. And it's all set up here ready to go. So we've seen how to create a Vex and we've seen printing them out. We've seen pushing things to the back and stuff. Just as a quick recap, it looks like let mut v equals vec bang of 1, 2, 3, let's say. You could also create an empty vector. You could create an empty vector a different way, like this if you wanted. And then I've declared all these as mutable, so then we could say later on vec.push, like the value 42, or more realistically, push 4, then push 5. Print out the value of that vector. Hop in here. Nope. There. Cargo run. Ruin. Cargo run. Doesn't know what type all of these are. Why is... Okay, Rust Analyzer's woken up. Okay, cool. It's saying, hey, I don't know what these vecs actually are, so I'm just going to say they're vecs of I32s. Oops. Cargo run, 4, 5. Right, I initialized it later to be empty vec. Bring this one back. 1, 2, 3, 4, 5. Fantastic. I'm actually just going to take a second as well to make sure I don't end up putting anything behind my camera. I have a little terminal in the corner to remind me. Okay, cool. Great, so we can push things. We can index into a vec. So I can say print out the 0th element of a vector, and that gives me the value 1 over here, like you'd expect. You can print out the 4th value, that gives me 5. You can print out the 5th value and get a crash, like you would in many other languages. A more robust way to index into a vector is not to use the array syntax here, but to say .get. So if I say .get instead, you'll see I get an option back, right? An option with sum 1. If I ask for the 4th thing, you'll see I get sum 5. And when I ask for something out of bounds, I just get none. So we're back into option land, and we can deal with this kind of error gracefully. Cool. We can also go through a vec. So we can say for x in v, let's say, get rid of this line over here, say print out x 1, 2, 3, 4, 5. Fantastic. Cool. And that's going to be like, that'll get us most of the way. So we want to find the mean. This is our first exercise here. We get a vec of numbers, tell us what the average is. Right, so as a reminder, the average, if I have 1, 2, 3, 4, 5, then the average of this list is going to be 3, because you add up all the numbers. 1 plus 2 plus 3 plus 4 plus 5 is 15. Is that true? Yes, equals 15. So sum equals 15. And then you divide that by the length of the list, which is 5. That gets us our average of 3. But if the list, say, was 1, 2, 3, 4, then the sum would be 10. The length would be 4. And then the average would be 2.5. So I've said we might want to return a float. Okay, so let's say let our sum be equal to 0. And let's say it's a mutable sum, a sum that can be changed. We say for number in the vec, add on to that sum the number that's there. And then at the very end, we're going to return the sum divided by the length of the vector. Now, fortunately, we can get the length from this, return sum divided by the length of the vector. And again, it's Rust. We don't need to write return. We can just have this expression at the very end. Now, this isn't going to work. We're going to find. We're going to get an error here. And I want to have this error pop up quickly because you're going to probably see this a fair amount. And I'm going to show you a bad way to deal with it, but it'll just be a bad way for now, which is that it's an expected F64 found. Okay, that's not the one I was. Just give me a second. This is the error that I want. Give me the error that I want to show them. Okay, give me that I want to show them. There we go. That's the one I wanted to show. Borrow of moved value, vec. So what's happening here is that when I say for each number in the vec, this acts like a move. I talked about moves at the end of last week's lecture, where basically, when we have some kind of owned type, like a vec, like a string, then sometimes when I say like pass that to a function or set another variable to be equal to it, that induces a move. It moves out of that value and it's no longer valid. When I say for element in vec, that actually moves vec, right? It's moved here. And the reason it's moved is so then we actually get this ownership. We actually end up moving each of the values inside the vec, into what we're using here. But, you don't need to worry about that so much for the moment. There's a neat trick, which is that calling len on a vec doesn't move out of it. So we can just say at the top here, let len be equal to vec.len. So say call this at the beginning and hold on to that. Just remember what it is. Down the bottom, use len down here. And you'll see that this now works and compiles. If you see this kind of thing happening in your own code, this is just a neat trick to get around it for the moment. We also see that length returns this usize. Again, there's robust ways to deal with this, but I'd like it to be quick, as is one of those kinds of things that you look for when you're trying to make your code more robust. Look out for as, and then, make it a bit cleaner, like using things .into or .try into, like we've seen previously. But I'm gonna leave it like that for now. Okay, so now this is returning a number. We want to really do like integer, not integer division, but like floating point division. So I had an F64 here before. I need to explicitly, it's the same kind of thing in a lot of languages, say sum times 1.0. Let's say like sum as an F64. Get rid of the times 1.0, that was silly. And then this length here we can also store as like an F64, like that. So just treat these as floating point numbers so we can deal with these decimal cases like such. And hopefully if I use, let's say I write println, find the mean of 1, 2, 3, 4, 5, like this, equals something, find the mean of a vec of 1, 2, 3, 4, 5, like that. We run this, we see it's equal to 3.0. Great, and that's what we were expecting before. By the way, if you want to do something approximately the same as this, there's a really nice shorthand, which I'm going to be using to do that, which is debug find the mean of 1, 2, 3, 4, 5, like that. You'll see if I run this now, it's basically saying the same information. This is here and this is here. It just also gives you the file and the line number, which is quite convenient as well. you can even then use that value. So if I wanted to debug, I think vec.len is giving me like the wrong value, I can also just throw a debug around there, and you'll see it'll print out that debug as it's running and still work. So debug is a really nice tool in Rust to help debug your applications. The difference between vec new and vec of empty of this like empty thing over here, absolutely nothing. So use whichever one you like the look of more. If I go back to 1, 2, 3, 4, let's see, is it dealing with the floating points correctly? 2.5 seems correct. Fantastic. But we had a message in the chat. What if the length of the vector is 0? And the answer is we get nan, which is a fancy floating point thing. Floating points are standardized. Rust really couldn't deviate from the floating point standard, and so null has made an appearance. It is kind of a tragedy of floating point of IEEE 754. IEEE 754. If you're interested in that, 1521, COMP6991 talks about it quite a bit. And so yeah, this is like a reasonable thing. What if the vec is empty? So how might we like to deal with that particular situation, right? And the answer is like we could, have a panic going on, like we could crash the application, we could write some documentation and say the list must be non-empty, like important, you need to, do this. Or we could try and bake into the types that, hey, maybe there's some cases where this isn't valid. So if we say this is going to be an option, like this, then say if vec is empty, return none. And the very end here, if things have gone well, give back some value. This is now, a new way of working. We get 1, 2, 3, 4, 5 is some value 3, 1, 2, 3, 4 is some value 2.5, and empty vec gives us just none. So this might be a way that you'd like to implement this. Say that this, this function may not return a value in the case where this vec is empty. What is the exclamation point that's around the place here, like in debug and vec? It means it's a macro invocation, and we'll talk about macros in week 7. Week 7, we'll talk about macros. In Python, statistics error mean requires at least one data point is raised. Yeah, exactly. So, and raising exceptions is not clear from the function's signature, the type of the function. There is one language, Java has something called checked exceptions, where it is clear in the type signature, but it also has this other kind of exceptions where you don't actually know what a function might raise, might throw. We'll talk about that a little bit tomorrow as well. Cool. So this is, I think, a reasonable implementation of this for now. There's certainly improvements that could be made, but it's demonstrated most of what we wanted to look at, I'd say. Just as another exercise, finding the median. The median is sort of like the average, but what you're looking for is the middle element. So if I had 1, 2, 2, 3, 4, what's the middle element? Well, right in the middle here is 2. So this would end up being 2. If I have 1, 2, let's say 1, 2, 4, 7, something like that, there is really no middle element. It's these 2. And so you end up just taking the average of those 2. So you'd get 3 here, right? So the middle element is this pair, and take the average of the pair. That's how medians work in maths. So find the median. What's the median as well? This is the kind of thing we should be thinking about. What's the median of an empty list? And I think it's reasonable to say, well, the median doesn't exist for an empty list. So I think it might be reasonable to take this same similar approach over here and start with an option like that. So this here would just be none. Okay, so if vec is empty, return none, like that. Now, this middle index is going to kind of change our logic depending on whether the list has a well-defined middle or not. So an easy way to check that is check if it's even. So we can say if vec.len, I wish Rust had a is even like this. That would be really nice. But the usual approach suffices. If vec len mod2 is equal to 0, so this is if it's even, this here is if it's odd. If it's odd, we could say it's quite simple. Just get me the middle index. This has length 5. We're trying to find the middle index of 2. 5 divided by 2 happens to be 2 because integer division rounds down. So I could really just say give back sum of vec of the vec.length divided by 2 as a float, like that. And now you can see Russ is immediately saying, hey, you haven't dealt with the even case, you know, compiler error. Yes, I know, I'm getting there. It's okay. In this case, we would like to say, where it's even, let the, let's say like the lower middle be equal to vec of vec.len divided by 2. So 4, length of 4 gives us 2. That would be the upper middle. So we really just need to subtract 1 as well. Like that. This here can be our upper middle. So the 2 variables in the middle. And then a neat little trick. Why not use find the mean over here that we've used already? So we can give back find the mean of a vec of lower middle and upper middle. So because we already have a function to give us the average. And this actually works as is. Find the mean may or may not return a value. We may or may not return a value. Realistically, we would like to say the mean is equal to this dot unwrap. Like we're expecting that this must be the case. In fact, you might like to write an expect and say this is exactly why. This is totally fine to do. And then once you've unwrapped it, give back some mean, like that. And we ensure that this code path never really leads to a none in an unexpected case. But as a shortcut, in theory, you could also just write, you know, delegate to find the mean. Are we assuming it's sorted? Let's say yes in this case. We're not, like, if we weren't sure it's sorted, that's totally fine. We can say vec.sort over here as well before we start. And that's a nice function to have. It sorts in place. It's worth knowing. So it'll mutate the vector. So let's do that. What do you think of giving find the mean something like the vec1 data structure from the vec1 as input, so, which is always guaranteed to not be empty? Yeah, that's another option we can have here, which is instead of having just taking in an input of a vec, we don't have vec1 in Rust, but you could write, say, i32, like first element being the i32 and the rest being a list. Now, because we always have to provide this, right, there's no null that we can have for first, you know, to call the function, you need to have a first value. So it would look something like 1 and then 2, 3, 4, 5, 1, 2, 3, 4, and this example just wouldn't work at all, right? You'll see no errors on these ones, error on this one. And so you absolutely can build this in at compile time, but it ends up being a little like less convenient. It's often that you won't see, even in cases where at least one element is required, you won't see people writing it like that just for the convenience factor of using it. And so there is a balance that has to be made between usability and, you know, how much we can really check at compile time. I mean, the logical limit of how much we can check at compile time going to we're checking literally everything that the program fulfills a certain statically defined contract is theorem proving, like formal methods kinds of programming, which certainly has its place and is very valuable, but not for all code because it is a massive overhead. I think the I'm trying to remember. I think Trustworthy Systems at UNSW put out what they believe was their factor of difficulty in terms of how much more difficult it is to write formally verified code than just standard code. I think they said, this is total memory, so take it with a grain of salt. I think that they said either 100 or 1000 was their factor, and they were aiming to get towards 10. That's just off my memory. Someone might be able to look it up and find the exact, you know, quotes. But right, the point here is that there's a trade-off between writing code that is, you know, where certain is going to be correct and how difficult it is to write it, and it's about finding the balance that works best for you and, you know, your team, your company, whoever you're working with, really. Cool. So I suppose we'll just quickly test this out as well. Of course, Rust does have like unit testing capabilities and the likes, but it's not what we're going to get into today. 1, 2, what were my examples? 1, 2, 2, 3, 4. 1, 2, 2, 3, 4. And my other one being 1, 2, 4, 7. 1, 2, 4, 7. And then, of course, let's try out the empty list as well. So we get 2, 3, and none. 2, 3, none. Looks like it's working about as expected. Okay. Now, there's this exercise I want to do called longest equal run, where we compare different approaches, particularly imperative, functional, and a mix of them. But this example really deserves its own time, so I think we'll leave it for tomorrow at the moment, and then we'll just focus on talking about string. We probably won't even do the hash map exercise. We'll just talk about a hash map, and I'll let you have that as your own exercise. But we'll just give strings and talking about hash maps their own due time, and then we'll come back to this example first thing tomorrow. What if the vec only contains one number element? I think that should be fine for both of them. Let's say we just had one value 42 for each of them. I believe the correct value for each of these cases would really just be, median would really just be 42. So 42 gives 42, 42 gives 42. Given it's the middle value for the median, and it's also the average value just being the only one. So those seem to work correctly as well. But it's a good case to think of, especially if we're trying to, properly unit test these units, these functions here. Cool. Okay, so let's talk about strings. String. Okay. Now, some important notes. Strings are UTF-8 in Rust. If you know what UTF-8 means, like if you know what Unicode is, then all strings specifically must be UTF-8. No UTF-16 going on. No UTF-32 encoded strings, although characters are UTF-32. Blah, blah, blah. If you don't know what that means, it's fine. If you don't know what UTF-8 means, it means strings can have like emojis, for example. And they can have, characters from international character sets. So you can absolutely have, like, say, the Japanese alphabet, European alphabets, like characters with, little accents and stuff. Like I was hoping they would have something close to the top here that I could use, but imagine, like, say, an E with like a line on top of it. Chinese character sets and the likes. We can use all of that in Rust. So they're convenient like that, but they rely on the fact that it must be valid UTF-8 text as well. So if you know what that means, you know what it means. If you don't, it's all good. Emojis work. Okay, cool. So we have two types, string and there's another one, stir over here. And you'll almost always see this as ampersand stir. See if they've written it. Oh, not you. Ampersand stir. Yeah, over here. It is usually seen in its borrow form ampersand stir. Like this, or like this, or in like one of these other cases here. Yeah, so you can see this function here returns this ampersand stir. We don't really know what the ampersand means yet. It's kind of like a pointer. We call it a borrow or a reference. And we'll talk about that a little later on. But basically, when you type double quotes into your program and you write some text in them, it'll turn into one of these ampersand stirs, in particular this ampersand tick static stir. Again, we'll talk about all of this week 4. And then there's this other type, capital S string. And there's actually a whole bunch of other string types. There's things like OS string. There's things like C string. There's C stir. There's OS stir. There's path buff, right? I don't mean to like overwhelm you, but Rust has a whole bunch of different string types. In fact, there's a meme that I quite liked. It's like how programmers see strings. Rust. I'm gonna see if here we go. I found it. Oh my gosh, why does it have to be a Reddit preview? Okay, well, it is what it is. This is the meme here where it's like, before using Rust, strings are a char star, like in C. after using Rust, there's like all these different types that might represent a string. We'll come to understand a good chunk of these throughout the course, but they all sort of mean slightly different things, and it's interesting to have that distinction available in Rust. In any case, where you'll see these ampersand strings usually when they're being passed into functions. You'll see the capital S strings usually when they're being passed out of functions like this. They work kind of the same. To create a an ampersand stir, again, you can just do like hello, like this. That gives you an ampersand stir. If you want to turn that into a capital S string, then you can use string from that, and that will end up doing what you want. We're going to talk about all of that quite a bit later. Let's implement a word count, which just says how many words are there in this string. Now, you might go, oh, I could solve this in my own language. I would go like for C in the string, like for each character in the string. Let's do like a to-do at the bottom here. And you'll see, stir is not an iterator. I can say iterate me across the characters of the string. C here is a character. I could say like if C dot like is equal to a space, or C is equal to like a new line, or C is equal to a tab, or all these kinds of things. And then you have a counter function, but you got to check if it starts, like if the whole string starts with a space or ends with a space. Those don't really count for an extra word. You can imagine this as a whole bunch of calculations where you turn it into quite an imperative solution that it really spells out how to do the whole thing. But we're going to take a more functional approach with this one. We can say something like string and then split the string up based on something. So split, let's say we had a string that was like hello world foo bar baz, like that. If I said split on a semicolon, then this would basically give me hello world foo bar baz, like this. It won't actually be a list like an array. It'll be something called an iterator. We'll talk about iterators tomorrow. But splitting allows us to take one big string like this and split it up into all its components. And there's actual different variations on split. Things like split, I could say split at an indice, like split at index 5, for example. Or I could say another really good one is split once, where it just says, split on the first delimiter, and then this will give me a tuple with just the first and last part. So I could say before, after, using pattern matching like this, right? So the before part, the after part, because it returns if I look at split once, oh, not that one, split once over here, it returns a tuple of 2 strings. These kinds of things can be really helpful and handy. Read through the documentation and see if something's useful for you. In our case, we do have something useful, string split white space, which says splits a string slice by white space. Let's look at the docs. Split white space over here. The iterator returned will return string slices that are subslices of the original string slice, blah, 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 separated by any amount of white space. And they have some examples that are tested here as well. A good thing we can see here is Mary space 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 had turns into Mary and had. It actually joins all these spaces together. So if I see Mary had a little lamb and see that gives back Mary had a little lamb, that looks quite convenient for counting spaces. So I can say string split on the white space, that gives me back, all the individual words separated by white space, and count them up. Done, just like that. Split on the white space, count it up. Now, of course, there's a lot of details going in here, right? Like split white space, I'm sure was not like an easy function for them to write. In particular, if we look at what they would have had to write here, self.inner.next. So there's like a split internal. We'd have to follow this whole rabbit hole down where blah blah blah. But someone's had to write the code somewhere to do this logic. But if someone has written the code for you to do the thing that you want, it might end up being a good idea to take advantage of that and keep your implementation simpler. Cool. Tons of things you can do with strings. Just have a brief read through the different functions available here, and you'll pick up a lot of stuff just as you work on Rust. You'll pick it up passively, just reading random bits of code. Yeah, so on and so forth. Excuse me. In particular, if you want to work with the individual characters of a string, .chars is your friend. It lets you sort of separate a string into its individual character parts. You can do things like count them up. You can work on each character individually. It uses, again, this iterator trait, which we're going to talk about tomorrow. So we'll leave that for now. Yeah, that's like strings. We're just talking pretty vague at the moment. Just making sure, you know, roughly like here's the taxonomy of them and a few things you can do with them. Finally, there's hash maps as well. Again, I suggested we're probably not going to write any code with hash maps today. But if you've used a map or a table or you know, any kind of key value store before, these will work pretty much how you expect them to. But we can just look at this example to get an idea. You can see they create a new hash map called book reviews. They declare it mutable so that they can insert things into this hash map. So insert key value. And these key values can be different types. They have a hash map of strings to strings, but they certainly could be like strings to like a number. Maybe it's like the rating of a book or like the number of pages or something like that. Or a struct with a whole bunch of information. Any key type, any value type. And they insert Adventures of Huckleberry Finn is my favorite book. Grimm's Fairy Tales is a masterpiece. Pride and Prejudice is very enjoyable. And The Adventures of Sherlock Holmes is I liked it a lot. So this is like their reviews. You know, review some books. They can say, check if the book reviews contains Les Miserables. And if not, then, you know, we've got these reviews, but this one isn't. So contains key, can check if something exists in there. You can remove things from the key value store. And then we could say, you know, get me this key. So get Pride and Prejudice, get Alice's Adventure in Wonderland. And that will return us an option, right? An option of the value. P, K, and this value over here, V. Because, you know, you might say, get me a book that doesn't exist in there. And it'll tell you, here's the, you could say here's the value, key value, right? Print out key value. Or if it's not in there, you'll get some none back and then print out it's unreviewed. So using match here to work with the hash map. And you can also look up a value for a key just using the like index operator like we've seen here. But again, like a vec, it'll panic if that key doesn't exist, like if the index is out of bounds. And quite nicely, you can also iterate across a hash map, and each element within a hash map will be a tuple pair of the key and the value. So you can iterate over everything, and you know, print them all out like this. So that's quite convenient. If I go and click run, it'll put it into the Rust playground for us. We can then click run and see all this output that comes out here. So definitely play around with that stuff. And hash maps, yeah, they're pretty common. They're quite useful. There's things like the entry API as well to make, you know, to write some particularly clever, more functional code. Yeah, just have a read of this kind of thing and play around with it, I would say. In Java, when you override the equality thingo, you generally also override the hash code for stuff like this. Do we also need to do something similar in Rust for hash maps keys? Oh, bruh, the docs say it. So that's a really good question, and I'm actually just going to show that off right now. Let's say I have a custom struct student that has a name, has a ZID, and has a WAM like this. And let's say I wanted to use students as a key in a hash map. Let my hash map be a hash map of students to, like, I don't know, anything. Student to string, whatever, equals hash map new. What you're going to find is that when you try and say my hash map dot, let's say mute my hash map, hash map dot, wake up, insert, hello? Right, exactly. When I try and I was like confused about the exact thing I'm trying to demonstrate. When you try and insert into the hash map some like student value, you're going to see, hey, I won't let you insert into this hash map because student doesn't implement eq, partial eq, or hash. Basically, in order for something to be a key in a hash map, you need to be able to hash it, and you need to be able to compare, like equality wise, check if two different keys are equal. Internally for a hash map, this is quite important. And so the trick to solve that is using our old friend derive. So I would write something like derive partial eq hash, like that. And it's going to say, I don't know what hash is, probably use std hash, like this. And oops, I put a exclamation point in there for some reason. And this is a problem with floating points. I was like thinking about this, and I was like, I'll come back to this. Some things can't be, like, because of the floating point standards, they don't have total equality. It's kind of a long story. If you try not to use a floating point number as a key in a hash map, because it's just not going to work properly. And this is sort of a problem in all languages, but Rust forces you to not be able to do it. That if you really, really know what you're doing, there are tricks around it. Like you can have like a my F64 kind of type that wraps an F64 and, you know, so on. I can help you through that if that's something you really want to do. Just ask on the forum. But now that this student can be used as a key, I could write something like, you know, student with some name, with some ZID, insert that with some string from hello, for example. Like that. And this will be happy. So if you want to use a custom type as a key in a hash map, you need partial eq hash, and those can be derived automatically by the compiler for you. There you go. Okay. I mean, we're at the end of the lecture. We're at 55 past, so let's basically call it there. To recap, we talked about pattern matching quite a bit. Hopefully we have a lot of stuff to explore with pattern matching. I'm not expecting you all to understand it all and have learnt it all. I just want you to understand some of the ideas behind it and know how to get started with playing around with it yourself, trying it out. We talked about optional values and looked at a few different languages and just, you know, spoke a bit briefly on that. Didn't get too in depth because, you know, we'll save some of those more intricate discussions for a little later, and we still have like just a lot of intro stuff to get through. And then we did a bunch of work with Vex, you know, playing around with lists, talked about strings, talked about hash maps as well. And we've left some stuff with iterators and comparing imperative and functional approaches for the first thing tomorrow. So that's roughly what we looked at today. So I'll stick around as long as anyone has any questions. Feel free to just ask in the chat. And yeah, literally as long as questions keep coming, I'll keep answering. Thank you everyone for joining, and we'll pick up on I promise you this will actually be quite a fun little exercise to play around with. So, you know, do come tomorrow again and tune in for this coverage over here. It's quite fun. Yeah, I'll catch you tomorrow. Okay. Hashtag overwhelmed. Yes, it all moves very quickly at the beginning of the course. And so totally cool with like people being overwhelmed and feeling like there's a lot going on, because there is, and that's okay. But we have a lot of practical exercises to try and help you get comfortable with everything. And the expectation isn't that you're understanding everything. I'm really trying to demonstrate stuff for you to get a vibe of Rust, see what it sort of looks like, and be ready to start experimenting on your own. And that's where the learning will really come, I think. So much of programming learning is really by doing. I think it's probably the most efficient way to learn, but it's hard to learn by doing when you don't even really know where to start and you don't know what Rust even really looks like. So I'm just trying to write a bunch of Rust code and walk us through a whole bunch of code to get us familiar with the vibes of things, and then you'll find that you know what to try, you know, fall over, and then how to pick yourself up and keep looking. So totally cool to be overwhelmed. I get this like every term, but by the end of it, people go, you know, it was tough. There was a lot to learn, but you know, I got the vibe eventually, and yeah, you'll hopefully be feeling a bit better soon. Cool. Thanks everyone for like coming out. Okay. So again, as always, questions. May I ask why I can't get my exercise score? I think a student mentioned at the beginning of the lecture today that the exercise marking is it's not working correctly. So literally, you know, once I finish this stream, I'm just going to send a message to the admins and go like, hey, we'll just like check up on this. So it's not your fault. We'll get it fixed up soon. Slice pattern docs say, within a slice, a range pattern without both lower and upper bounds must be enclosed in parentheses, as in a ... To clarify, it is intended to match against a single slice element. Any idea what this means? Would it match against multiple elements otherwise? Okay. Okay, I see what it's saying. What that's saying is, and this is a very specific kind of issue, is let's say we have a let me think about this. Let's say we have a list of integers 1, 2, 3. Let 1, 2, 3. Let x's be equal to 1, 2, 3. I then want to match x's, and for reasons unbeknownst, I kind of want this to be a slice, so don't worry what that means. They're saying, now I could match this and say match on where this is. Actually, no, let's leave this as an array. I match this where this is 1 underscore 3, and then that does something, and then I have a wildcard case that deals with the other scenario. So this is fine so far. What it's saying is, if I want to say match, let's say 1, let's change this to 1, 2, and then any number here. If I wanted to say instead 1, 2, and then just any number that's greater than 2, like 3 ... like this, I think, then this is potentially conflicting with it's potentially conflicting with the like slice syntax like this, basically. Now this specific scenario, these patterns, x ... patterns in slices are experimental. Interesting. So apparently that hasn't quite landed yet, but it's like that. Now what's it saying? A range pattern without both upper and lower bounds must be enclosed in parentheses to say it is intended to match against a single slice element. Is this because, can I write let foo be equal to 10 and then let range be equal to foo ... I don't think this is something you can do. Oh, maybe it is. Okay. So if I go print out debug of this, I think we're coming up to it. Yeah, okay, so it does. So you can define a range like this, basically, where you say, I have a variable number, and I create a integer range out of that by saying foo ... So saying like 10 upwards, basically. Just, it's the same as this, but with a variable. And then I want to match on this, like that same thing, use foo ... like this. What it's complaining about is it's saying this might in some cases match against, like, if I wanted to say what the number 1 and then like the rest of the slice. To clarify that I'm talking about a single slice element, I need to put this in parentheses to say I really want, let's say, like the number 1 and then this element to satisfy the pattern of this range, as opposed to the number 1 and then like the rest of the slice with this foo here. I'm not 100% sure what this syntax is representing, but it's complaining that that might be a conflict. Now, it's worth mentioning, it's a great question, it's an interesting topic. This is not a conflict I've ever run into in my years of programming Rust. So this is going to certainly be very niche, but yeah, I think that's the general idea of what they're getting at. I think oh yeah, this thing, don't worry about this thing. Don't worry about this part. I was just looking at testing whether this actually works and does what I thought it was. So this panic is just coming down here from there. Yeah, that's exactly right. So don't worry about that part. In fact, it would probably be wise to even comment this out for if students want to like play around with this themselves. So just to show, this should still run and do all the stuff. And yeah, I really just wanted to check this line here. Cool. Another question to end off. If I make my own equality operation not derived, should I also make my own hash thingo like Java, or can I still derive it and Rust does some super magic stuff somehow? Good question. Let's try it out. So impl partial eq for a student. Get rid of this derived stuff over here. Implement the missing members. And you can see it's actually really nice when you get it to fill out this. Usually, most of the time, it'll just fill it out with a to-do here. But when it's something it knows, it actually fills the default, like a good implementation as well, which is kind of nice. Impl eq for student. This actually is just a marker trait, so there's nothing to implement there. And the hash still works, it turns out. And so you can certainly implement some things manually yourself. That eq can also be derived as well, if I don't want to write that bit here. So you can have a custom partial equality and a different hash. And if you want to look at what that hash function turned into, you can use cargo expand, which you won't have installed locally most likely. You can do cargo install cargo expand to get that command, or you can just use 6991 cargo expand because I have it installed on CSE. And this expands all the macros and stuff like that, and you should see this is what it creates out of impl hash for student. You'll see it creates a function hash, which basically just, you know, mutably hashes this name and ZID field. So if your equality, you know, maybe names don't matter, which would be a reasonable thing for a student to say that names don't matter, only ZIDs are important for both equality and hashing. It's important to realize if I just derive hash, it's going to hash everything in here. So then you might want to do your own hash. And so exactly, yeah, it might cause some problems if they go out of sync. So it just depends on exactly what you're doing in the individual case. If you want things to be automatically derived, it's important to know at least approximately how it's going to be derived. In our case with hash, it's going to consider all the fields. So yeah, there is like an important sort of correspondence between hash and eq. I'd be surprised if it wasn't even mentioned in the documentation here. Implementing hash, blah, blah, blah. If you need more control, then implement hash yourself. When implementing both hash and eq, it is important that the following property holds. So k1 equals k2 implies that the hashes are the same. You don't need to worry about this if you derive it, but violating this is a logic error. The behavior is not specified, but it will not result in undefined behavior, basically. Yeah, cool. A side note, I've been wondering why your Vim is so user-friendly. As in, like, how my Vim looks like this. It's mostly just stolen configs from random people. I don't even know what's in there these days, to be honest. I'm gonna bring this back quickly. And Vim. There's just a whole bunch of random stuff in here. Theming, fuzzy find. I don't even think I use the fuzzy finding stuff very often. Like language highlighting, like Rust Analyzer stuff. LaTeX doesn't matter. You know, I've got some like random things in here. You can use any of this stuff if you really want to. I also like using arrow keys, which is gonna make a lot of people very upset, but it is what it is. So on and so forth. And there's this thing here, Alt Enter. This is a really good shortcut to have, and it's not that easy to find like the right thing to put here. So this might be helpful if you're trying to set up a similar kind of thing. Yeah, you can poke around through this and take bits that you like. I like to keep it relatively simple, to be honest. Cool. Any other questions before we wrap up? I will, as always. Yep, this is good. As always. What did I change here? Oh, I added the matching stuff in, of course. Okay. Add in the let go 3 materials for you all to make use of. in the Lec Materials GitHub repository. So go play around with that code if you're interested. Any other questions? Lazy is much easier, honestly. I'm not sure if lazy is like another tool or something in Vim. I'm not really much of a text editor person, so you've probably already gone beyond me. And your text editor choice is Minecraft, Book, and Quill. That seems like a very reasonable choice, especially for programming. I like it. I'd like to see using that as like an actual text editor by poking into the like the save file of the game or something and pulling out the wherever it must store that actual text. That'd be quite interesting. Cool. I'll wait for like if I get any more questions in like the next 30 seconds. Oh, it's a plugin manager for Vim. Gotcha. Yeah. I know there's like 2 or 3 dozen options. I think I'm using plug. Yeah, I'm using plug. Yeah, I'm sure it probably is a lot better. Mine sort of just is what it is. Cool. All right, I haven't got any more questions, so thank you for coming out, everyone. I'll see you all tomorrow in the same place, up on YouTube. Everything's there for you to play around with. We'll do some fun stuff tomorrow. In particular, we'll be continuing on with these examples, which should be really fun. There's a lot to argue about there, which is always tons of fun. And then we'll be talking more about error handling, particularly with some other languages in mind, and we'll use some match and some other fancy operators. There's one which is the question mark operator. It's really quite cool. Cool. Other than that, thanks everyone. I'll catch you all tomorrow. All right. Thanks and bye-bye.